first on stage will be Marc Cosdras. So I'm very happy to have Marc with us. Actually, Marc was the one who convinced me of the merit of this approach. I remember a nice lunch we had together with Andy Cooper in Brussels, I don't know, maybe 5 years ago. That really, for me, it was really a discovery of the potential of this approach. And so I'm very happy that you were able to be with us today. And I know also how excited you are about what we could do together between over the Atlantic Ocean in order to have also our institutions moving in the right direction. So please.
Yeah, thanks very much, Philippe. First of all, it's a real pleasure to be here. I made it a priority to come, even though I just traveled in November. I came back in May, and now I'm back in June, in a time when travel's not so often. And first point, travel, so important. Having those conversations, those dinners, it's so important to be able to move this forward, because it's only through these events that we get some awareness and visibility, and that's at all scales. We saw, Fedor, you talked about bottom up. Well, how many people started at the atomistic and they're doing the bottom up and things? I had to start at the top down, and we only started at the top about 2015. I'll go to the next slide. 2015 is when they had COP21, and they decided that they had to solve the world's climate change problem. And it took about 2 years for them to say, well, what are we going to do about it? So in 2017, I was asked to represent Canada and on the issue of materials, clean energy materials. And so in 2017, they formulated what clean energy materials would look like through the Innovation Challenge 6 of Mission Innovation. Okay, that's fairly recent that they even started to think about it to build the ecosystem. And what their goal was by 2021, which we just passed the first 5-year mandate, was to double the spend. And that was something where they always refer to Bill Gates, but Bill Gates, people like him, the investors that feel that there's got to be some things happening at the government level, do something about it. So federal government said they'll spend more, 23 member states. And last June, they renewed our mandate. So the government mandates another 5 years. I have a sort of a job for another 5 years, even though I retired, Philippe knows. And things like this, the missions that they're creating or that are under development have another 4 years to deploy. And if you look at it, clean hydrogen at $2 US per kilogram under the mission. Sorry if you can't see it at the back because it's at the bottom, but the US has indicated they want hydrogen at $1 per kilogram. Okay, fantastic. Aspirational goals, maybe. Stretch goals, doesn't matter. Carbon dioxide is another one that's really important and identified as a mission. But how are they going to do it? I always hear after the fact that they're going to need material support, not in the mission itself. They need material support. So how do I tool up? How do I get activity to build a network to be able to support them when they need it? Okay, so what we've done is move from Innovation Challenge 6 in the first mandate to Materials for Energy. They wanted a rebranding, they wanted something new, but we're really the same entity. We're just a network of people. We're trying to build a network of people that allow us to help those missions solve their problems. I talked about travel. In November, I met people from VS Particle. In May, when I came back, I went to their labs and had a look at their equipment and things. And I believe they have a great solution here to help us be able to achieve things from a synthesis perspective. And I know how to put that into a bigger complex system. And I'm going to show you as I proceed. You'll see also that I'm very cognizant of Big Map. We know that the guys in Battery 2030 and Big Map are handling battery materials in the most effective way, according to what the vision of IC6, the Innovation Challenge 6 was. Of course, we heard from Jens, who talked about the work at Erlangen and Nuremberg and saw how much he's doing there. Very impressive from a network building perspective. And then we have project data, and I'll talk about project data. Project data was after the Mexico City event that defined my international activity. We published the report in January. In March of 2018, 3 months later after publishing the report, we got $8 million for project data in Canada. 3 months. When was the last time you saw a project launch from scratch in 3 months? 8 million. Not bad. So if you look at what we're actually trying to do, and we have, I'm around this all the time. Materials Acceleration Platforms is the name of the report, published in January 2018. It gives us a bit of a roadmap to understand what we're doing. We're really trying to make sure that 23 member states, and especially the ones that are part of IC6 and M4E, know a little bit about the words Materials Acceleration Platform, Accelerated Materials Discovery. That's how Philippe found out about it. That's how others are finding about it as well. But we also want to make sure that we build in self-driving, autonomous materials laboratories. We've heard some of those words today. And we need to make sure that everybody understands that's something that's the same thing, and that we're working from all of that activity. What's the goal of the workshop report? Acceleration by a factor of 10. We didn't know what was possible, but we anticipated that at least 10 times acceleration. We have examples. Atenary's got examples. Jens has got some great examples. Other ones are out there. And so it's really important that we use those examples. And I use Jens's example, his lab's work often. We'll see it again, because it's so important for people to see what's going on. Of course, we're doing closed loop synthesis, characterization, computation. It's done with automation. It really is a combination of all those things. And if we don't look at it as a combination of everything in that left graphic, we've missed the point about a fully integrated map or self-driving lab. And one of the things that I wanted to do in this conversation is make sure that we heard it today, not only is it a new discovery of materials, it's a device at the end. We have to make a device. It could be a battery, big map. I saw their map. So they have an operational map that makes cells, and it can make cells of diverse materials. Go to Ohm, have a look at it. Go to Erlangen and Nuremberg, find out what it's like to make a device and test it in situ. So that's the reality. What's the urgent need? Okay, I work for Natural Resources Canada in Canada. So I'm the government representative to address the mandate of the government from a clean energy perspective. So we have climate change. We all know unprecedented climate change challenges, escalating rate of change, myriad solution pathways. There's 100 different things I could be funding, and I have no funding left if I give everybody $1 and hope that they can solve the world's problems. So what do we have to do? Accelerate. Material supply chains, critical materials right now, critical minerals is becoming extremely important to governments. And I'm paying attention to that. So I'm looking for funding to be able to move forward when you talk about iridium. Of course, iridium's expensive, iridium's rare. How do we use less of it? Critical materials tells us we have either that or replace it. And so that's another mandate coming down from the government for us to actually pay attention to the kinds of things that this drives. There's less materials available in the ground. It's harder and harder to get that stuff. What are all the things from a sustainability perspective that we heard about earlier that leads us to do certain things? And what about 50 to 80% of the cost of clean energy is the materials? It's unbelievable. The good thing is, and why should we do it now? What's the urgent need to do it now? We have the tool, maps, self-driving labs, autonomous labs, whatever you want to call them, it doesn't matter. We actually have the tool to address these things. So concept to demonstration. This is project data. And so as a first demonstrator, that they had 3 years, $10.8 million in total, but we gave them $8 million to do it. They started from scratch. They built the system that then went out and did in a cycle time of 21 minutes, could cycle through and do the data points that they're showing up in the top right, run number 1, do it again. And it was a question I was going to ask. What happens, Loic, if you run the thing from scratch with no knowledge again and again and again? Do you get it 6 experiments? And the answer is reasonably well, yes. And you can see run 1, run 2. So I had that example, and I was going to raise that as an important issue. And then that experimental space. Yeah, it's just a couple things here on the chart itself, but the experimental space can be massive, and it exceeds a human's ability to look at that. So super important stuff. And now what do we have to do next? We still have to develop these platforms, the techniques, the AI algorithms, the stuff that Loic talked about, like the stuff that Dassault talked about. And it's super important for us to keep building up these pillars of automation, AI techniques, and data. How do we handle that kind of stuff? But the platform implementation is where I do a lot of my work. So what's that workflow? And a couple of the presentations talked about workflow. The map design approach is another one. In Berlin earlier this week, we talked about, do you build a map or do you buy a map? So I can go and buy an entire ChemSpeed, or I can buy an entire Thermo Fisher system to do what I want to do. Might be $1.5 million, might be 20 million. I don't know, right? I might go build it, and I might spend 20 million on the labor to build the thing, right? To get it working. I have to really make cognizant decisions about that. So how do I do the design approach? Diverse map architectures. If I took a VS particle printer and I put it in 3 different labs, how does it behave? Making the same catalysts. We're thinking about doing those things, actually. That's why I went and visited with VS Particle. And the multidisciplinary skill development. Okay, we heard it, what, 5 times today? Because they get educated, they leave, then we have to start again, we get another person. And there's some things that I'll talk about that. Okay, materials to devices. I'm going to stress materials to devices over and over and over. And yes, there absolutely is your lab from the other end. I saw that you had the picture from the far end the last time, I think. But the idea is materials to devices. And it's all about learning about the processes that go along with making these materials, these devices. And then that aging testing. I mean, you couldn't have asked for a nicer system to talk about. When I travel, I use it quite often. Big Map's another one. They're tooled up and they're getting really close to having it. Their final characterization was down for repairs, but the thing exists. It's a big line of glove boxes and fume hoods and other things that allow them to go right to the device level. And then we have one in our lab. And I'll tell you, and I mentioned earlier because I was asked, how is the development going? Well, I'm actually pivoting because our synthesis proved not to work. So I can't solve the problem that I was hoping to solve, which is a low cost, earth abundant, non-toxic thermoelectric device, material and device. And my synthesis method doesn't work. You talked about challenges, right, Jens? And the fact is we're pivoting, and we're going to take that same system that deals with high temperature melt, solidify, and heat treat, and we're going to study heat treatment of aluminum scandium conductors. So an aluminum conductor to replace copper, because copper is 3 times the density, okay, lightweight aluminum, and it's 3 times the cost. A 10 times driver for someone to put aluminum conductors in a traction motor, because they're going to need 20 million of them in 5 years. For Europe, another 25 million for North America. And if we could lightweight them at lower cost and still get performance, which I was a co-author of a paper that says we can, then we need to get that material optimized. Our system can do that. So we're pivoting right now to optimize that material. And that's a great thing about maps, self-driving labs. Once it's able to do something, Jens, you moved from one organic system over to perovskites. And that transition was fairly quick, I think, right? But you're using the same backbone to do it. Pivoting is critically important, and that helps you to understand how to scale. Here's different things that we're working on. Map topics. So UBC is working on whole transport materials, membrane electrode assemblies for CO2 conversion. We've got a process map with telescope and UBC spinoff, but lithium from Brine Solutions. You can see all of the examples, aluminum scandium wires in there. because it's the one that I'm transitioning to from thermoelectrics. But look at the other topics that I've already spent time on, developing workflows, help different people actually work on these types of things. Flotation in mining. We had an inquiry about flotation in mining. I've been thinking about that. How diverse a way of applying what we do. But what else should we be looking at? Talk to us. Ask us what else we could do. And it's really because I'm working to build the network. I'm top-down governments trying to build a network so that we can get a sustainable ecosystem in the future. And that's where it's really important. So I just wanted to say, what material do you want to work on? Let's see if a map can be thrown at it. Building from IC6. This is something that we really need. So what other things should we work on? Ideation, white paper solicitation. There's a cell press in Matter, a call for map ideas. It's due on July 15th. But we want to have as many ideas coming in on what we could do with a self-driving lab as we can get. And in the end of August, we're in just at the beginning of September, Acceleration Consortium, it's the University of Toronto. So you'll get these links when you get this presentation. But they have first of all, we have a GCMAC, German Canadian Materials Acceleration Center, week-long workshop for training, skills development, and map development. So we've got all aspects of the German Canadian Materials Acceleration Center, a bilateral collaboration that's allowing us to look at electrocatalysis, but we're looking at all the maps to learn from them, because you can learn something from no matter what that map is making. The Acceleration Consortium is a development where they're focusing on skills and education in the academic realm. What did we say was a gap? So they're focusing on this in collaboration with things like GCMAC and in collaboration with our network within Materials for Energy in mission innovation. And then we have things like STORIES. STORIES is the storage research infrastructure ecosystem. What we're trying to build is a sustainable ecosystem. That's getting infrastructure available to everyone so that they can go and visit Canada, US, and then we can take people from Canada and bring them to Europe to access the infrastructure that they have here, that kind of thing. Setting up these collaborations is critically important. So communication and coordination, it absolutely needed. Coordination and implementation, so workflow development, data ontologies, we heard about it all throughout the day, and more maps. We need more of them. We need more of them out there to test them, to drive them really hard with all the software and all the simulation and modeling, and move from that. Here's something that we did in Canada. We've got a $60 million investment in a new building. The second and third floor are specially designed for maps, self-driving labs. 6,000 square meters that's there for materials development. And that was something that we got since mission innovation started. In fact, mission innovation activity drove the government of Canada to invest in this lab. Super open lab so that we can bring people from anywhere in the world. We're trying to figure out how that's going to work with security and everything else, but anywhere in the world. And we built a lab that models what's going into that building, at least 500 meters squared. Industry alignment, EMIRI and URA AG. EMIRI, we know. URA came to us because the German Materials Acceleration Center, they saw a workshop on it, and they came to us and said, we have 2,500 industry people, companies, 2,500 companies. Many of them probably want to know what you're doing. And so we're signing an MOU with them. Funding, coordination, and leveraging. So from top down, we need to do some work with the science-based departments. In September, we have mission innovation, 7th ministerial. So ministers from all the countries come together. I want to hold an event, and we're trying to get the US DOE, the National Science Foundation, ARPA-E, DARPA, NIST, so DOC and Department of Commerce and Department of Defense, all interested. And if we get them, we'll have US, Canada, Europe, really, really building to the point where we have a good ecosystem. So we've got a workshop that we're planning for September. the main thing that we're really moving for from a top-down approach. Make sure that governments understand what accelerated materials discovery is, and make sure they hear what we heard today. So the white paper, Philippe, at the end of this is going to be critically important. And that will just be a summary, so I'll just leave it at that.
Thanks a lot, Mark. Thank you very much. So we are definitively late on schedule. So what I propose is that you keep your question, because I would like still to have a small really panel discussion. And Mark, I will invite you to come back for this panel. And now let's move to the next presentation. So Mariona, it's your turn. So really introducing the French EPR, if I'm not wrong, program, which is called DIADEM. So we are very pleased to have with us today Dr. Mario Margione, if I'm not Magnone, sorry, who will really introduce the scope of and the content of this program. And this will be completed by a second presentation from Thierry Deutsch from CEA on the numerical parts of the program. So if you could make it, both of you, in 20 minutes, that would be great, so that we do not go too much after the
Thank you. I will try to do it in 10 minutes. So thank you. So as you said, so I am Mario Maglione. I am belonging to the CNRS, the National Center in France for the Research. And I am co-leading this program with Frédéric Schuster. Maybe many of you know already about Frédéric Schuster. He's in charge of the transverse program in CEA about materials research. And we have also Professor Alexandre Legris, who is a top director of CNRS. So what about DIADEM? Sorry, to be short, so I'm sorry, I have no pointer. Okay. So DIADEM, this acronym in itself tells you a lot. It's a discovery, acceleration for the deployment of emerging materials. So we are in between discovery and deployment. So maybe a little bit far away from what we heard this morning, which means I am very far. This program is not directly connected for applications. It's more in between, I would say, academy, CNRS, and first step of deployment, which means CEA. That's why these two entities, CNRS and CEA, have been in charge of launching and running this program. So the first acceleration is not exactly in materials, is the way we got it. I mean, the way we got the support. We already heard about Mark, how fast it was to get the support. For France, it was also quite fast. In May 2021, the French government opened a call, very broad one, every topic, lasers, biology, everything, and we applied for in May 2021. In September, we had an interview with the international committee, and in October, we got the news that we were selected. 4 programs, starting with 70 in May, 4 were selected, among which we have DIADEM. So it was quite fast, and I can say now, in May, after 1 year, the project started. Some of the projects, they get the funding. I don't know for other countries, but for France, it's quite fast. So that's the first acceleration, the way we got it, okay? So I will skip this because we heard a lot about the challenges that we have to use artificial intelligence to speed up, to accelerate the deployment of materials. That no interest here. What are the international program with which we are close? I mean, the first one, I think everybody knows about this Material Genome Initiative. The second picture of Barack Obama here after yours, which was launched in US in 2010 okay? Which was one of the first program in between academy and industry to accelerate material discovery by artificial intelligence. From that time, so we all know that papers, patents started to speed up a lot. And so what we see here in Material Genome Initiative is something that now we have seen already a lot of time this morning. At the European level, so this starting in US. At the European level, what we have also some program. I'm not giving the full list. I mean, I'm giving the list of programs with which we are close, I would say. So one of the first was in Switzerland, the program Marvel, which started in EPFL in 2013. We have at the European level, we heard a lot already about the European Open Science Cloud. We have in Germany a program which started last year, which is called FAIRMAT, and which also we had some exchanges. And there are about 20 running European projects dealing with more or less topics which are close to artificial intelligence as applied to material science. So this is a list of this top. I don't want you to see all of the list. At the top, this was not prepared. I mean, by chance, I put a big map at the top, okay? So you have here a lot of European programs during the few last years and still running programs in which artificial intelligence has some interest or not, okay? And in which French labs, CNRS, CEA, and university labs are involved. This is to say that there are already a lot of initiatives to support this topic. In France, we have already some projects running, which are mostly through what we call GDR, which means networks of lab, university and CNRS labs dealing with this topic. And Grenoble here is one of the key part for this artificial intelligence as applied to material science. And we have also the site in Paris-Saclay, where Frédéric Schuster here is, where we have also ongoing project on that. So our goal is to assemble in a way all these existing things in a way to build some, let's say, coherent work in between academy already in between academy and deployment of materials. So we got for that 85 million for 8 years, okay, starting from 2022 up to 2030. So how we did that? So the implementation was first focused on platform. Most of the budget will go for platforms, okay? So we have here, we see at the center 3 types of platform: high throughput synthesis and shaping of materials, high throughput characterization, and modeling numerical design of materials and processes. Well, these are the 3 main platforms we want to build, and there is no hierarchy. I mean, it's a circle, which means you can start from modeling and then synthesize. You can start from synthesize, then characterize, and so on. It is just turning. And what's important in this picture is the green part, which will be described in more detail by Thierry Deutsch, which is a numerical platform, which is helping all of this experimental platform and numerical platform to go together. Okay, so that's the core, that's the main part of the budget. And our mission is to establish these platforms in the next few years. To show that these platforms are efficient, we'll need projects. Projects which will be research projects focused on showing the efficiency of the platforms. Okay, so we selected, it's really a top-down. With Frédéric Schuster and Alexandre Gris, we selected people. We did not ask everybody, do you want to be involved? We had few weeks, I would say, and we selected, okay? This is really the beginning, the art of the program is top-down. So I will not go into many details. This is the DIADEM. These are the projects that will show the efficiency of the platform. So I will not describe all for sure because of lack of time, but maybe if you, yes, if we have the second one, integrated approach of durability, it looks simple. We are dealing here with alloys. The focus of this project is to show that finding new alloys is a way to fight against corrosion. Corrosion, 3.5% of the world GDP is lost because of corrosion. In that case, we have to find new alloys, not in the standard way, which is mixing 100% of 5 different metallic elements. We call it high entropy alloys. And just by trial and error standard way of research, this will simply be impossible. So we need artificial intelligence to screen all of this very extended phase space, 5 different metals, and you mix all of them from 0 to 100%. Okay, so let's imagine how many of these alloys you can get. And the focus is try to use the platform to find the right alloy which is efficient against corrosion. That's one example. We have another one maybe which is called amethyst, okay, which is more dealing with polymers, but not the polymers we heard about this morning, maybe polymers including biosourcing of polymers, but also polymers in which will include particles, inorganic nanoparticles. Okay, so this means the extension of the phase space again is huge. Artificial intelligence is again needed. I could give you many examples of that, but all of this project, we did not focus on one type of material, neither we focus on one type of application. I mean, it's quite extended again. This is to show that the platform, the core is efficient in many different cases, not only in single one, okay? So that's the way we built it. Yeah. Okay. Oh, something is. Oh, sorry. Yes, we added some 3 new projects, and all of this will start in 2022. That's fast. The budget for this, all of this you have, is 45 million. So we are assembling CEA, CNRS, and several universities, 7 universities in France. Maybe you can recognize name. And as I said, the Grenoble one is among them. The management is not important. What is important in this picture is a scientific advisory board in which we will assemble people from international program. I was very happy because during the building of DIADEM, I had exchanges with Jim Warren, the leader of the Material Genome Initiative, Claudia Drexel, the leader of the Fermat, and Nicola Mazzari, who is the leader of Marvel. And these 3 people, they were very enthusiastic. They said, okay, we'll join this committee to help you having international view on the project that will be selected. And we'll have input from industry at this point. The global planning also is not very interesting. What is interesting is that we will open calls from 2024. 32 million will be dedicated to this open call. Once the platform will be started, we will open call to every lab in France. But obviously, international lab companies can be involved without getting grants, but getting support and getting cooperation with this French lab, okay? And the last row is very important. We heard a lot about education. We need to educate, as was said already, master students, but we really need to educate already senior scientists like me. And the goal here is to have education and all lifelong formation. We have 40,000 researchers and engineers dealing with material science in France. We don't want all of them to be educated to artificial intelligence, but at least 1/3 of them by the end of DIADEM should be knowing something about application of artificial intelligence, which means 1,000 of people. And this is the part of the budget which is dedicated to that. And that's all for my global presentation. And Thierry will now give you one example.
Thank you very much, Mario. Yeah, so let's move directly to this second part of the presentation of DIADEM. So Thierry Deutsch, I think, Thierry, you are based here in Grenoble, part of CEA. So I will let you introduce yourself and what is your role here in this program. Okay, that's it.
Okay, so I will develop the diamond part of DIADEM. So diamond for data management and infrastructures for artificial intelligence, modeling, optimization, and numerical design. So as you can say, we have a lot of targeted projects. So the goal for us is to develop different platforms to help to use the different users, especially experimentalists. Experimentalists are not very don't know very well the numerical part, and we have also a problem of formation. So our goal is really to facilitate the use of the different numerical tools. So François Willem is a pilot from CEA, the energy department. Noël Jacques is a co-pilot and is here in Grenoble, is University Grenoble-Alpes. So what we want to do is to accelerate, as the other people, in fact, the characterization, advanced characterization mainly, and the modeling of materials. So for that, we will use AI to detect, classify defects, images, structure, and so on. So the second point is we want to facilitate the use, to democratize the different tools, the different digital tools, coupling simulation and experimental data analysis. In my part, I'm coming from DFT, so density functional theory. So I'm more theoretical physicist, but it's really important for us to have a coupling between this simulation, not only DFT, but also CALFAD and mesoscopic simulation, and experimental tools coming from different experimental platforms. So two use cases. The first is now we can, in real time, doing an automatic analysis of experimental data. In this case, you have a irradiated high entropy alloy, and you can easily have an automatic indexation of dislocation loops. And then you can, of course, do more processes as statistics and so on. But this kind of things is not quite common, but it's spread over now. The second point, maybe more focus, is about catalysis reaction. So Marie-Ingrid Richard, in her ERC Carine, now can image a single nanoparticle to understand the catalysis. So it could be platinum, and to understand different kind of catalysis. And the goal is, in fact, to image, to have some spectra, as you can see, doing at atomic scale reconstruction, 3D reconstruction, doing a lot of very strong operation with some simulation in real time. And now the next step, in fact, is because she has a very good database with this 3D reconstruction, she can directly recognize the different defects in nanoparticles, for instance, a loop, a dislocation loop, or other defects in surface, and then having an information, good information in real time in these nanoparticles, understanding the different reaction in presence of different gases as oxygen and so on. And these kind of things, even if it's quite fundamental research, I think this kind of thing after could be go to the industry. So the goal of Diamond is to develop first a digital infrastructure to store and distribute the code. So we have a plethoric amount of code because we have a lot of targeted projects. So for that, we need containers, and we use also workflow. The second point is we will generate a lot of data, and so we want to deploy a material database and all tools necessary for their exploitation. And this, in fact, then we will use to develop demonstrators. So the first platform is about code and workflow. So we have a large amount of codes. We develop our codes. In my case, I developed code big DFT in DFT. Now we have an application for very large system, protein, and so on. But anyway, but we have also other codes in different multi-scales. As you know, materials need to have studies in different scales, and so we have also different tools to simulate the materials at different cases. We have also data-driven on AI models. So we want to also to share these models. And last point, and not the least, we develop a lot of analysis tools because now we have a very large amount of data. For instance, in ESRF here, we have many terabytes per day and per lines. So it's quite heavy. So you need very strong, very good tools to analyze that. And the goal is to put this in a repository using the container solution. Container solution is a way to encapsulate our code with all libraries. So we want to have in a national level a repository of containers in a cloud solution to find easily these containers, to share and to improve it. The second point is workflow. Because now we're compiling a lot of codes, a lot of solutions, then we need also to share these workflows. So we will have demonstrator using the computer center here in Grenoble, GRICAD, and we will have a link with the DIADEM database for data. And our goal is really to facilitate the use of this different solution. The second database, the second platform is database. So as you know, there are different, there are already some platforms, so Nomad, Fermat, Matwerk in Germany, and Materials Cloud, which is related to Marvel in Switzerland. What we want is to build a French database, but for different kind of data. Simulation data for atomistic, mesoscale, and macroscale simulation, characterization in synchrotron, ESRF, Soleil, but also for different other kind of characterization as electron microscopy, FIB also really important. And for that, we need to develop a web portal, and we need also to standardize our REST API. And we will use Optimate, which is a Belgian solution, which is a way to address all these different databases. Then, in our containers, we will have all tools to address the different database and to import the data. And so we will have a strong link with code and workflow platform. And this should be based in TGCC. So TGCC is the national supercomputer. We will have, I hope, in 2 years, an exaflop computer, and we will use this national facility. So, in conclusion, so the objective is really to democratize the material clouds, so a lot, using AI-based numerical solution. We want also to automatize simulation and analysis of experimental data to enable, of course, high throughput, because database, for instance, if for some there are more than 10,000 components. We want also to collect, store, and interrogate materials data. And of course, all these things should be to accelerate the prediction of new materials with some targeted tailored properties. Thank you.
Thank you very much. What I propose to do now is just let's say, if you are not totally exhausted, maybe for just 20 minutes to go through a more open exchange between a few people and you in the room, or also you who are online. So I would really invite to join me here on stage, Mario for the French aspect, Marc for the more international aspect, Holger Rissen also from Helmholtz Association, who is the representative of the Helmholtz Association in Brussels on the energy activities, and also Professor Ilian Todorov from the European Materials Modeling Council, who is also with us today, and also maybe for the voice of industry, if you could come back also on stage, so that we have a quick wrap up, I would say, of what was discussed today, and also try to identify really what are the key action that we could take, and also really more concretely, what next? What could we do really to move a little bit in the right direction? So thank you all, and please take a seat. My first question, I think. My first question is very obvious. I think we already heard a lot about it today. But if you had to point out your top three of the others that we are facing, what would that be? So I don't know who wants to start. We heard about skills, mindset. We heard about also money needed really to build these infrastructures. What do you think is the most urgent hurdle that we should really target really to improve and to deploy this approach of material acceleration platform? Who wants to take it? Rui?
So maybe offering one thing for the industry, one thing thinking about the larger organization, right? So my first would be definitely the workforce, the developing skilled people and the quantities we need that can bridge between fundamental sciences and computer sciences to develop the tools and implement the tools that we need. But then thinking from a broader perspective, right? A lot of the capabilities I showed and my colleagues showed are extremely expensive. I mean, we can afford Tensor, right? A high performance cluster. Lots of wonderful people and smaller companies don't have. So all the efforts we saw on democratization, not only of the intellectual tools, but also the hardware capabilities, I think it's key to take the continent where it needs to be. I think some of the efforts shown are a step in the right decision, but we need a lot more, right? That to show that a person with the proper ideas still would have the same level of access to those tools as a large company would.
Thank you. Someone else?
I think that the skills development is a critical thing. We've mentioned it multiple times. Thanks for raising it. The one thing that we did do when we built the Center for Accelerated Materials Discovery and Innovation, or we're building it. It's done in April 2024. The universities are telling us they don't have space to actually demonstrate, to build maps and demonstrate this technology. So we're building space for them. They need infrastructure. You talked about the cost of the equipment. So we're aggregating a bunch of universities to say, if you get that, and you get that, and you get that, and we put it in one place, so a new building that allows you to aggregate the types of equipment you need, you actually have a place to train. Not a theoretical thing at the front of the classroom, but an actual hands-on training place. So that's part of building that ecosystem that will survive. If we don't do that, we're in trouble. And so Stories is an example of infrastructure availability that allows others to actually go and access the equipment and learn how to do this and integration. It's all very, very integrated. It's all necessary. All these pieces of the puzzle have to come together to achieve the skills development we're talking about.
Yeah, if you can maybe elaborate a little bit on Stories, Olga.
Yeah, I mean, Stories is only at the end of my short speech here. I mean, I think most important, I mean, I drafted a flagship proposal for materials acceleration platforms in 2019 or so. And what I had to what I had to realize is that I mean, we failed because people said, okay, we have not the excellence. And I would say in some other proposals, we failed. And again, the excellent part was badly marked. And I mean, what I see is also from the member states representatives for also the national contact points, they simply don't know what an accelerated materials platform is. So we talk with something or on something which is unknown to a large community. And this is the reason why we get this bad marks somehow, and the proposals are short. Okay, so, and overall, I think to move forward, we need to strengthen our networks between each other. The stories is in research infrastructure ecosystem, where I mean the Commission made in the last Green Deal call on Horizon 2020 offered 7 million euros and for access from industry to research infrastructures. And our focus here is mainly on materials. And we are connected with GCMEC and also with the Canadians. And the idea is basically to connect the Canadian and maybe US facilities with the European research infrastructures, set up a metadata data structure, which was also discussed recently from you. And the offer basically as a common interface to all the researchers having access to the research infrastructures, visiting us, but also for the research facility itself. So, I mean, the network is key so that we all stick together and distribute the information that the accelerated materials discovery ideas have some potential. And with this, I think we become stronger and stronger also in the reviews of the proposals.
For me, one thing that we will have to avoid in the next few years is dispersion. I mean, we have many people, many labs who can be involved. And for me today was very interesting. I mean, the example I got from industry, from Ulish, if this was successful, it was for me, as I understand, because a lot of support, a lot of money was put in the same place. And then after people, okay, it's no, you say no. No, I mean, for example, in France, as I said, we have 85 million for 8 years. If you divide by this many labs, there should not be so much at the end for each people. So the goal that we will launch in 2024, we decided this 32 million not to divide in too many. I mean, it will be 30 projects maximum. That's the first, avoid dispersion. And the next, I think, is work at the international level. I mean, we see these initiatives, which are in every country, and we have to work at the European level to show that the government have put a lot of money. It's a lot of money. There are efforts from industry, maybe at the European level, and then at the international level, we have to show that it's working. So it's complicated because we have not a lot of time. We have to make the platform running, showing that it works, and then convince the people to really support.
Yeah, and if I may, regarding your point, but maybe keep the mic because I have a question for you, and it's more related maybe on the question that on the part that was presented by Thierry. But the ambition of really collecting and building this big database for France that was presented by Thierry. My question was, why only for France? Why keeping still silos between countries and not trying also to work on how to connect these databases at the more broadly at an international level?
I think Thierry can answer, yeah.
Why? Because it's for France, because it's a French project. So the budget is French, but everything will be open. So it means that all people in the world could collect data from our database. And there are also already a database in Switzerland, so material clots in Marvel, and in Germany with Nomad for simulation, Madwerk, and so on. So another point is I talk about Optimade. Optimade is a way, it's an API, a common API to easily interrogate these different databases.
Thank you. Yes. Yes.
Maybe one comment from my side. I think it's important to have large-scale projects, but I don't think everything needs to be done with super large infrastructures. So the things we've demonstrated in our labs, because you mentioned universities don't have access to it, that's true. Things like line 1, the fully integrated line, is something that is really actually relatively hard to operate in a university context. But we have smaller lines, these spin bots, they're fully ready. They're commercialized even by a company called Cyprios. They can be bought, and you can do everything that the map has with these already. And I think what's important is that there's an easy in for many people. So some low cost option that actually the Bill Gates vision, put a PC on every desktop. I think that's kind of where we need to go. We need to have it widely available, and we need to actually make it very clear. And I think that also comes from experience of people working with it. What is the added value that we are giving? How are we improving their lives? And we have to do that on a low level to encourage them to actually get the data into formats that we can use it. And then, of course, at a higher level, we're going to need something to curate this data somehow and handle the access to this data.
Yeah, and also as a defense, so in Germany, there's also the platform Material Digital, which is completely, it's the same as the France initiative. So I think that's really a good point. So national governments, of course, try to want to spend the money on their own country. But I think if we are not able to connect within Europe, we have no chance in a global space. So I think it's a really important mission. It's okay if we start on a national basis, but we should align now during the development and not later if we are too distributed and too far away from each other.
All right, so let me add something here. One of the things I think you started this morning saying we cannot do it alone. And I think the most important thing in everything that we discuss is culture, changing how we think. You say it's talent and skills, but this we can train. We can take action about it. Changing culture is a little bit more difficult. It also leads to what Amir mentioned about the green dimension or the dimension of ontologizing, documentation, standardization, because all these databases, they don't need to be French, German, and so on. They're also not physically at one place. They're geologically at different places, bits and pieces of them. It's about how these things talk. And it takes a little work, maybe it's a lot of work that pays in the long term if we agree on common standards, because then it will be easy to query those databases. It's never going to be like Google. You ask for this material, it pops up. You'll have to pay. You can only expose the metadata of what the data is about. And also, I think you were talking about processes, ontologies for processes, but I didn't say anything about energy or, okay, there was a mention of toxicity, but let's say that each process takes some energy value. If you put that in, you can then go to business process decision-making of how much you invest and how much you get out. If you also have something about recyclability later or product life, you can actually optimize a product so that you know it can be used later or recycled more easily. And this is not something that people think about now, people implement, but it is something that we think about because I think it's important. A little work to put in to standardize or put as much information as possible. And then the artificial intelligence, machine learning, and so on, that is actually 70 years old. If people were to the session the other day, it can do the job to actually correlate end to end of how important it is to know what the impact will be eventually in industry or even to the society of picking the right product that is easy to recycle. Imagine an organic computer, use it for 5 years. It changes smartphones every 2 years. Imagine you can just throw it and it's biodegradable. It doesn't exist. What's probably not going to exist, but certain fashionable devices may exist that are biodegradable. So I think change of culture is the word, and this can be supported by networks. That has to be supported by governments. And also there is, you mentioned about German network, NFDI is one of the networks. And similarly now in the UK, we are setting up something called PSDI, Physical Sciences Data Infrastructure. I think each country is pushing their own way from a different point of view. But at the end, if you put that little effort to annotate to some extent almost everything that we produce, we will be able to talk to each other and extract value.
Okay, thank you. Building on your comments about sustainability and also echoing to what Amaya asked earlier, do you see really that these tools could also contribute to integrate all the safe and sustainable by design approach? You know about this framework, which is currently under construction by the European Commission, that they really would like also to implement or really to have all the materials community to build on that, really to focus on safe and sustainable materials, which means not only about the performances of the materials, but also the performances of the production, the use phase, the recycling phase. Is it something that you feel can be also captured by these tools?
I think that that's a super critical area for collaboration, right? Maybe the best area for collaboration because it's less competitive. I think we all would want to protect performance models for the chemistries we are developing, but the areas of ecotoxicity, environmental models, they are very time consuming, extremely expensive generating all the data to train those models properly, but they could exist for the benefit of the industry, right? That's one area in which academy and different industries could collaborate. That's a wonderful area for funding, right? Because for fairness, the same regulators that are creating that challenge to the industry could be providing us with the tools so we can generate models to make those products safer and be able to assess the products which are not without necessarily having to go to animals for testing.
Yeah, maybe about this. Yeah, there is at least one project in DIADEM where people are trying not only to have materials, digital twins, but also digital twins of the processes, as applied, for example, to ceramics, where ceramics needs a lot of energy because high temperatures, and using 3D manufacturing and very specific sintering, they could decrease the temperature by a lot. But for this, you have a lot of parameters that need to be put in the system. You have many parameters, and the processes itself needs to be digitally twinned.
Yeah. Yeah, I think I had a first question from Simon here.
Yeah, also to connect to your comment. So if we, from the beginning on, we think energy is part of every process, and of course resources or CO2 are also materials, part of the process. So at the scientists in a lab, we not think about LCA in the first way. But if we annotate the resource consumption of our process and innovations, and we put that into the same data structure that also LCA experts use, can directly find new results. So imagine you have a map infrastructure finding a process consuming much less energy than before, and that is fully described in a database. The next day, an LCA expert finds a new route for a new product involving the new process, and then he can directly tell the industry, okay, we have we found a way to lower the footprint. I think that's a tight integration. We do not think in the first way, but if you always add all aspects of a process to its description, and you're able to do that in the everyday's work, I think we have a very powerful connection to resource efficiency.
A comment I have here is, I mean, I think we should not focus on the materials development. We should focus on the applications, and then look what the application needs for materials. So I make not materials research just for fun, and as you said, as a researcher, for example, storage is a problem. I mean, we can produce energy in the moment on the Arabic Peninsula with 1 cent per kilowatt hour, so very, very cheap. So, but our society, what they need is a long-term storage. For long-term storage, there's no solution, as we've heard. Hydrogen might be a problem because iridium is missing to a large extent here. So there might be, I mean, so there are two ways forward. Either, I mean, we put the critical raw materials out of in the electrolyzers, or we have an alternative. And the alternative could be, for example, magnesium. or aluminium as the storage materials. And so, I mean, the future will make a decision on it.
Yeah, and there's something else that you said that was really interesting. Okay, we heard earlier we have multi-objective optimization. So we can actually look and do LCA, we can do energy calculations if the process is commercially viable. And I think it was you that said that the 2 to 4 times the productivity, one of the presentations we heard this morning, of actual solutions, right, of the solution. So it was viable commercially, and that's why it was economically important, and it's going to solve problems. So once you have a map that can, that you might develop it and say, well, I'll spin coat because that's easy. But spin coating doesn't do solar panel sized pieces very easily. We have to go to technologies like spray coating of some kind, for instance, that would allow us to do the area that we need. And so we're always thinking about that when we're developing map experimental workflows to say, how are we doing it? Then we can use the process knowledge developed through those processes where we're developing the map that actually is doing the scalable process. And we can start looking at energy, CO2, et cetera, and build it right into the optimization. We won't forget to do that. We have to build those things in, and that'll answer some of the questions along the way.
Thank you. Another question?
Well, more of two comments. So I perfectly agree with the comment that we should, so to say, top down when we look for a material. I mean, the application should define how we look for a new material. So, but academics usually tend to be expert in the material. And then I try to squeeze out, find an application for that. So, I mean, there's a flagship for graphene, and what they're doing is trying to find application for graphene. But the other thing I wanted to say is I mean, we touched upon ownership, because data and having access to a map is really a crucial competitive advantage. So we should also discuss who owns the data that's been generated in a whole community, and who has, so to say, the right to use it, to develop it, and also a common map, who have the user access and user rights to that.
Yeah, and I'll comment on that really quickly, because in our program, Mission Innovation, I don't even have money. I'm just aggregating a network that allows us to look at these things. And there's lots of maps that are in development. I'm developing some maps. So I find critical materials money and go set up a piece of map. Then I find energy money and try and aggregate that to build out the kind of system that, Jens, you have in Jülich. And so we're making those maps, we're developing maps as a tool. Our IP is the development of the map, not the development of the material that might sit on that map that I then move to another material, and a company comes in, works on it. They bring in their knowledge, solve their problem, and leave. I just learned how to run that map. I just learned how to design and build that map. So my IP is in the platform. The materials specific IP we're trying to keep as a separate thing that is brought in and left with, even the foreground IP. That's what we're trying to do in my expanded lab in Canada, so that all companies can come and trust that when they use it, it's separated, secure, etc. That's our approach from the start. And we're trying to get everybody to agree to it. We're hopeful.
Yes, I cannot resist making this question even broader about access rights. I appreciate that this workshop is mainly technical, but we also had a question of money here, and taxpayers' money, and there is an issue of politics. How open is open? Because not everyone is our friend, and not for always. And it is perfect to say that we like collaborating within Europe. And it may be IP for which you pay, but you have the right to access. And now the UK is no longer in Europe, in the European Union, but I'm happy to collaborate with Ilian. And we are happy to have a guest from Canada. How open should we be? Because frankly speaking, I'm very disturbed by this open access policy of the European Commission, which tells us now to make all our papers open access to everyone. That's the question. Do we all want it to be this way?
Who wants to take this one? I think it's going much broader than just materialization platform, but it's true that that's totally valid here. So
I'm going to say one thing, and I have to be somewhat sensitive to the fact that I work in the Department of Natural Resources in Canada. Okay. We are designing a lab to function to really open up that lab space for people to access. The first partner we set up, however, was Germany. And we have the German-Canadian Materials Acceleration Center that we're trying to eventually use. Well, we can use my lab and the small lab in my building today, but I'm building a building to make it accessible. We will form collaborations and there will be agreements that allow countries to enter in, and they will certainly be the first people we work with. Though we'd like to be wide open, that may not be the case, and there may be decisions that have to be made along the way. That's all I'll say. Okay, but there will be specific things. You said you would work with Canada. We will probably work with you, which means that collaboration is good from the start. I'll just say it that way.
But definitively, data access, data management. I think Guillaume, you mentioned export control also, which is a key issue. It's not a detail that needs to be taken into consideration, of course. Yeah.
Each data, the LCA, material cards that describe the behaviors and that we're using in modelizations are valuable. We don't give to someone else like that free. An LCA because it integrates the process of how the company makes the product. So it's hard. What we need for all these pieces and for some data is to uncrypt them. To uncrypt them, to find the right partner, to trust, and to have the right solution in terms of software. We have that for modelizations. Material cards that are the digital twin of a polymer, for example, are in fact in the software editor, uncrypted. And if someone wants to use it, you authorize it and you have an agreement like that through the editor. But it's uncrypted. You don't have even to let open and that he see everything. It's maybe don't see the data, but he can use the data that are encrypted. So it's at the European, like the battery passport, each piece of value chain will not see the other value chain's data. It's uncrypted also in the system. Blockchain can be used or whatever, but you at the European Commission, they need to define the policy and the rules and say, this is common data, this is not, and you have to encrypt in different way. And by this, you structure the right of access beyond the country or the European zone.
A short comment as well. 200 years ago, about 1815 or so in Germany, they decided, the Prussian government decided that IPR issues are not an issue, so it is free. And the reason was that UK was ahead of Germany. And because they freed it, I mean, and they stole a lot of IPR from the UK at that time. But I mean, in a very short time, they achieved a lot of knowledge, and they were basically equal. You know? So they were peer with the UK, and in some parts they even took them over. So, and I think the idea here is from the European Commission, if we have open access, so that we can bring our society forward. And it's also true that there are some nations who try to benefit from this, making no research. But I mean, for example, the nuclear weapons and also other information, they were able to extract this information from the US and others also under high security rules. We have to keep this in mind.
I'm afraid we will have to stop because I think we could go for the whole afternoon. First, before thanking you, I would like to give the floor to Eric Peters, who is our chairman in EMIRI. so that really maybe we also identify some very practical actions. You were talking about a white paper. I think that's a good idea. What should we do now? What next?
I will keep this very short. So I'm very happy to be here because I think this was a fantastic day. I think above all, this is about the societal challenges that are coming at us. It is about that huge transformation to a green economy, to a more sustainable society. Europe calls that transformation the green and digital revolution. And I think today was maybe for me the very first time how that word digital really came to life in that green revolution. We will not make it happen without the digital part, I think. I do want to thank CEA for hosting us, and because I think this is a great facility to do this. You know, at the end of InTech with so many people in person, this meeting was 100,000 times better because we were in person. And I think it's great that you are all here and that you stayed until 2 o'clock. I'm going to make an attempt to summarize the meeting in 6 points, just my own summary. And I'm not as smart as most people in the room, so bear with me. I saw some amazing examples. That's the first point. So we are on track. This is not some future far-fetched thing. I really saw some amazing examples from both industry and academia and government labs in how much progress we've made. I also saw amazing levels of investment, right? This is not coming for free. And I think that is really driving for me more than anything else, the need for collaboration. There is nobody that has deep enough pockets to do this on their own. And it's collaboration, I think, between industry, academia, RTOs, small and large companies, you know, government initiatives, like what you talked about, Mark. I think there is huge opportunity for collaboration. We talked a lot about data. The first 2-3 hours, we talked about the quality of the data, making sure data is codable, making sure it's structured in the right way. We ended up talking about the value of data and how we're going to share data. I think both are very important. One of the biggest points for my summary is that it's not about materials, it's about devices. I think you used the word devices. I think you talked about applications. It is about designing those things that make society better and can be used in real life, scaled and deployed, you know, across the world. And of course, advanced materials are an enabler for that, but it is about the device. And then my last point is, and this is what is making me dream and making me really happy to be here, we are only at the start of this. I mean, we are going to have a digitally native workforce coming anytime now, right? I have a 15-year-old. She's never seen a world without computers and smartphones. I mean, when those people get through university, this is really going to change something, and it's really going to help that cultural change that we talked about. We are at the start of artificial intelligence and machine learning. I mean, we are really at the start of neural networks. And I think in our lifetime, we will have quantum computers. So think about how all these things are going to accelerate what we talked about today. So this was my short summary. I do agree with Philippe and others that we should probably try to have a real summary from this meeting going out and publicized. I think that would be very powerful. And you know, we will try to do our best at EMIRI to make that happen. But I'm sure many others in the room that would be willing to help out with that. So thank you all for having been here. It's phenomenal. I mean, in my day job, I'm managing sustainability, and I'm realizing it's going to be maybe easier than I thought with all of this stuff happening here. So I'm fully intent to leverage, you know, any good thing coming out of all this beautiful research. So thank you all for being here.
Thank you, Eric, and in particular, thanks to all of the speakers. I was quite late in putting really this workshop in place, and a bit nervous that I could get the right speakers. And at the end, I ended up with too many very good speakers. So we were not, so that's why the agenda was a bit too heavy, but I really wanted to have all of you with us today, because I think it was really a great opportunity for not only discussing, but also identifying some key priorities and what should be our targets for the next month. Thanks a lot, and so we still have networking time now. So there's some light food available downstairs. So yes, and very important, you know, EMIRI is celebrating its 10th anniversary this year. So when you leave the room, there is a small gift here on the table. So don't hesitate, please take yours.